In a previous lab, we looked at 2D contact and the restitution properties. In this example, I want to look at a 3D contact instead of 2D contact. And in 3D contact, we have the values of stiffness, dampening, and friction. Now, you may want to read the help explanation of these parameters. So when we are doing a motion analysis in Inventor, it assumes that our bodies are rigid bodies. That is, there isn't deformation in the bodies. So although we have static bodies that don't deform, we can set some values to represent the properties. And stiffness then is the resistance of the elastic body to deformation. And then dampening is a function of the stiffness of the part, or the two parts in contact, the penetration between the two parts, dampening value, and the normal velocity between the two parts. And then we also have in the 3D contact joint properties the number of contact points that we want to visually see. We can display some vectors for those contacts and some other parameters, and friction as well. Okay, so I have this simulation set up to play for 5 seconds and do 500 calculations. Now this behavior is really sensitive to the number of calculations, so you may need to increase the number of calculations in order to get the correct behavior. I have a stiffness value set up as 1000 newtons per millimeter, and then a dampening value set up of 1 newton second per millimeter. I'll have friction initially, I'll set that as 0. Turn off the contact points. I have all contact points displayed with this value as 0. I'll then go ahead and play the simulation. So the ball goes down, and notice that it will slightly penetrate the second part. Now it might be difficult to see, and then it just sat there. If I decrease this stiffness value, and let's go to 500, and I'll play that again. Let's change it to 100. It might be easiest to see if I go to a wireframe view. So I'm going to go to wireframe, and we see that the ball has slightly penetrated this base. Now I'm going to turn off the dampening. Let's put this on 0. I'm going to put this back up to 1000, and we'll play it again. So with the dampening set to 0, the ball will bounce back up. The calculations are a little bit slow. It's complex 3D contact. So the issue is finding some appropriate numbers between the stiffness of the materials and the dampening to get the behavior that you would observe in the real world. And probably the best way to do that is through physical experimentation with real world objects of the materials that you're going to use. Let's put this up 100,000. We'll make this real stiff. So these two numbers interact with each other. Alright, and then I may want to see those contact points, so let's go to the contact points. I wanted to say one thing about friction here before we do that. If I put this ball spinning, which we'll do in a later lab, if the ball is spinning but I don't put any friction on here, it will still only bounce straight up and down. So if I put a friction value though, when it comes in contact, the friction would cause it to go either left or right depending on the direction of the spin. So I'm not going to use friction on this one, but notice also we can put friction as a value of the input graph. So if we want to start out with a static friction and then we want to represent a motion friction, we can set that with the input grapher. So if I tell it I want to see the number of contact points, and I have to know which order that I selected these in. It looks like I did base and then the ball. If I want the contact points on the base, and let's say I just want to see one contact point, and I'll go ahead and play this again. Now it's real subtle where it shows that contact. There's a little dot there. Hopefully you can see it. Let me stop this and rewind and play it again. So right where that ball comes down into contact, there'll be a dot. So it shows little dots here each place that comes in contact. And I can do that for each of the components. I may also want to display a vector, and you can change the color of that vector at the contact point. I'll go ahead and play it again. So initially the vector is real long, and then it reduces as that bounces. I want to do this at more calculations, so let's do this at 1,000 calculations. So part of the challenge is to do enough calculations to capture whatever information it is that you want to capture, but also do the analysis within a reasonable amount of time. So the more calculations you do, the longer it's going to take to run. So that was 3D contact, stiffening, and dampening.